Now, permutations, this is another thing that we've already seen. What we're going to highlight here with permutations, what a permutation is taking a bunch of objects and putting them in an order. So the order matters, and that's going to come up later, because when we learn about combinations, combinations are similar, but the order doesn't matter. So far, if you wanted to write all the permutations of A, B, and C, well, you could just start listing them. You could maybe make a tree diagram if you wanted to, if that would help you. And you know there has to be 6 of them because we have 3 decisions to make. We have 3 choices for our first letter. Then there would only be 2 left and then 1. So when you're listing them, if you use the fundamental counting principle to start off with, you'll be able to say, okay, I know that there's 6 of them, and then it's just a matter of finding the 6 different permutations that there are. We've seen the formula already. We remember that compared to our spaces, the R represents how many spaces, and the N is the number that you start with. So if you had 10p2, that's the same as 10 times 9 with the spaces, but with the factorial and the formula, that would be 10 factorial over 8 factorial, and if you expanded that, you could see why it's equal to 10 times 9. Some special cases, if you have npn, that means you're starting with n and you have n spaces. According to the formula, you get n factorial, and in this particular case is where the 0 factorial comes up. And you might remember from before when we defined factorials that 0 factorial doesn't fit the normal definition of factorials because you can't start at 0 and go down to 1. But 0 factorial is defined to be 1. It's just equal to 1 by definition. And one of the reasons it is so that this formula works in all cases. Find the number of ways a program in which the order matters of 4 pieces of music can be made from 10 pieces of music. So if you're using spaces, we find that often with these questions, we will use the spaces strategy more than we'll use a formula. So we have 4 decisions to make. You have 10 choices of song for the first one, then 9, then 8, then 7. And this is the same as 10p4. So if it was 100 pieces of music and you had to choose 30 of them, well, then the spaces might be annoying, because you have so many spaces to make. And then 100p30 might be easier to work with. Again, there's a place for this in your calculator, so you can find that the same place that you find your factorial button. Find the number of permutations of math. Well, that you could just do 4 factorial because there's 4 letters and they're all different. 4 factorial. This is the first time a permutation question sometimes throws people for a little bit of a loop because you're used to putting people into desks. You're not used to putting desks into people. And because when you make spaces, your brain might think, oh, I'll make a space for every desk. But the problem is if you make 12 spaces and start with the number 5, you're going to run out of numbers before you fill all the spaces. Again, with the spaces strategy, you have to think, what does a space represent? It represents a decision. What are the decisions being made here? Well, student number 1 comes into class and has a decision where they're going to sit. How many choices does that first student have? 12 choices, because there's 12 desks. The second person walks in, they also have to make a decision where they're going to sit. and they look around, and there are 11 desks left, because we don't want to put 12 in there because it would be pretty awkward if you sat on someone's lap during math help. So there's 11 desks left. And then third person, then 10, then 9, then 8. So this could be represented by 12p5. If we think about our class, 5, 10, 15, 20, 25, 30, there's 33 desks in here right now, and there are 5, 10, 15, 22 of you here. And just finding out how big that number is, so I could have a different seating plan until I die with you guys. If we had one every probably minute, we could change seating plans, and we never go through them all. I'd like you to change this so it matches what we called it in our textbook. In our textbook, we called this permutations with identical objects. And so in these situations, all of a sudden you have letters that repeat themselves. So if I switch the two G's around, it still says egg. So our strategy for counting these ones, if there are identical objects, we say, well, how many letters are there in egg? There's 3 letters. And if all the letters were different, it would be 3 factorial. But because we have a repetition in there, we have 2 identical objects, which are the G's, we divide by 2 factorial to divide out that repetition. In Assisipi, 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. But now we have 3 S's, so we divide by 3 factorial for the S's, 2 P's and 2 I's, 2 factorial and 2 factorial. And objects that have only 1, you don't need to divide by 1 factorial, but it wouldn't make a difference if you did. So everything that is identical needs to get divided out. So one way that identical object questions come up is just with words. Okay. There are some other times that it comes up here. Again, you read the question, and what you're looking for as the hint is, are any of these objects identical? Well, in this case, this person sold 3 of model A, 4 of model B, and 2 of model C. How many ways could they be arranged on the street? So if we think of writing this out, one arrangement would be all the A's first, then all the B's, then the C's. We have identical objects. And so we divide by 3 factorial for the A's, 4 factorial for the B's, and 2 factorial for the C's. I'm going through these rather quick because we have seen all of these questions already once from our textbook. John lives 3 blocks north. And 6 blocks east of school. 3 blocks north, no, he's over here. 6 blocks east and 3 blocks north from school. How many different routes can he walk home, assuming he always walks closer to home? So using identical objects, you could say, well, one path is walking north 3 times, and then E 6 times. So using identical objects, be 9 factorial over 6 factorial, 3 factorial. And we also learned how to count this one directly when we did this question to begin with. When you could say, if I'm starting here, there's only one path to each of those corners. In fact, there's only one all along the straight routes, because the only way you could get from here to here is that path. But then for this one, there's going to be 2 because we add up the corners. And 2 plus 1, this will be 3, 2 plus 1, 3, 1 plus 3, 4, 3 plus 3, 6, 3 plus 1, 4, 1 plus 4, 5, 1 plus 5, 6, 7, 4 plus 6 is 10, 10, 20, 15, 21, 28, 35, 56, 84. And if you would do 9 factorial divided by 6 factorial, 3 factorial, you would get 84 as well. For this one too, you can just put a line through that. We are going to just talk about this strategy and call it grouping. And this is the first time we'll run into something new. And some of you came across this question when we were working on our whiteboards the other day, and you came up with a way of figuring it out, and now you're going to see a strategy that would allow you to figure it out quicker. So sometimes we want things to be grouped together. And the first example that we have says, I want to arrange my math books. I've got 4 calculus books, 5 algebra books, and 4 geometry books. They're all different. I want to put them on my shelf, but I want to have the calculus books together, I want my algebra books together, and I want my geometry books together. How many ways can I arrange them all? Well, what we do is we first make the decision of how I want to arrange the groups. Can you see that it could be, you've got calculus, algebra, and geometry? How many ways could I decide that first? 3 factorial. I could put calculus first, then algebra, then geometry, or I could put algebra first, then geometry, then calculus, and so on and so on. So my first decision is I decide, how do I want my groups organized? And since I have 3 groups, they're all different, it would be 3 factorial. Once I've made that decision, then I go, well, if I chose my calculus to go first, how many ways could I arrange my calculus books? That's my second decision. And so since there are 4 calculus books, they can be arranged in 4 factorial ways. Followed by algebra is my next decision, and then geometry. Well, my algebra can be arranged in 5 factorials, my geometry in 4 factorial ways. And since each of those were decisions, the fundamental counting principle tells us we need to multiply them all together. So the grouping strategy is a strategy when you want things to be grouped together. That's the first decision that you make, your number of groups. And however many groups you have, you do your number of groups factorial. Then you look in each group separately and arrange that group as well. So the question you had in your homework that was similar, and these are different names, but you have 5 people that want to sit on a park bench. And Jill, it's springtime, Jill and Bill want to sit together. Birds are tweeting, everything's nice. So it becomes a grouping question because with the 5 people, Jill and Bill want to sit together. They become one group. So with the grouping strategy, the first thing we have to count is how many groups are there? And in this question, this is where a mistake gets made because a lot of people say 2 groups, Jill and Bill and the rest. But do the rest have to sit together? No. Jill and Bill could sit between Amy and Lee. Jill and Bill could sit between Lee and Tom. And so when we talk about groups in this one, there's actually 4 groups. Jill and Bill are the only group that have to be together, and each of the other ones are individuals. So our number of groups is 4 factorial. Sometimes people think of this as, instead of 4 groups, think of it as 4 people. Jill and Bill are just now glued together. They're like one person. You never see them apart. And then yet there's, so if you're arranging 4 people, well then it would be 4 factorial ways of doing that. The grouping strategy then says look at each of your groups and arrange them. Well, the only group that's more than one, I mean, we could put 4 spaces here. These ones are kind of not necessary because the only group that has more than one person is Jill and Bill. And the number of ways of arranging them, it could be Jill and Bill or Bill and Jill. And the rest, if you put numbers in there, would just be 1 factorial. That's why this part really isn't necessary. And 4 factorial times 2 factorial is 48. So there would be 48 ways that the 5 people could sit on the park bench if Jill and Bill wanted to sit together. If you think of gluing them together as one person, the Jill-Bill that you always see together, well, you could glue them right shoulder to left shoulder, or you could have glued them left shoulder to right shoulder. So that would make sense why that 2 factorial would be there. Okay, part B, things get a little contagious. And now, Lee and Amy also want to sit together. Poor Tom. Don't worry, Tom gets his revenge in part C. But now we have Jill and Bill together, we have Lee and Amy together, and Tom still by himself. With the grouping strategy, we would now say there are 3 groups. And the one group has 2 people, so they can be arranged in 2 factorial. The other group has 2 people, they can be arranged in 2 factorial. And you wouldn't have to put Tom because he's only 1, and he can't be rearranged any further. So the number of groups in total here is 24. Or the number of arrangements is 24. Now, Tom's revenge. All of a sudden, Jill and Bill must not sit together. And we're not going to worry about Lee and Amy. They could sit together. They don't have to sit together. They're okay with that. But whatever happens now, Jill and Bill must not sit together. You wonder why they come to the park bench anymore. You would think if something this drastic happened, it would be a very awkward sitting on a park bench anyways. But now we're going to count how many ways Jill and Bill must not sit together. And you did one similar to this. I think it was Amanda and Edna, right? And some of you figured out a whole bunch of different cases. If Amanda sat here, then Edna couldn't sit there. But this is a great example of where the not strategy works. Now, the not strategy says count all of them and subtract the bad ones, and you'll be left with the ones you wanted. Well, all the ways people could sit on the park bench is very easy to count. 5 people on a park bench, 5 factorial. If we want them not to sit together, the bad arrangements would be all the ones where they do sit together. And we figured that out in part A. In part A, we figured out that there was 48 ways where Jill and Bill sat together. So if we take 5 factorial, which is 120, and subtract the 48, we're left with 72 ways where Jill and Bill are apart. And since we already counted that bad way in A, this was a really easy way to figure it out. Okay? Now, looking at what I saw some people counted, and this is a good strategy as well, it works. They said, okay, there's 5 spaces, I'm going to put Jill here. Okay? Then this is not Bill right there. So there'd be one way Jill sits there. If this is not Bill, I have 3 choices, and then the rest doesn't matter. 3, 2, 1, 18 ways. And then next time, Jill sits here. Then this cannot be Bill, and this cannot be Bill. So if Jill sits there, 1 choice, then there'd be 3 choices of not Bill there, 2 choices there, and then 2, and then 1 for 12. And how many things do we have to count out? Whoops, that's too many spaces. Well, Jill could have been here, then Jill could have been here, then Jill could be here. You would get 12 again, and 18 again. If you add those all up, you get 72, just like before. But this takes a lot more space than the not strategy. So this is a good example where the not strategy works. But also in permutations and combinations, it's good to see that depending on how you think about the question, there are different ways of counting it and different ways that work. Which